So what was the most number of times you had to do integration by parts last night that you found in your homework? 2 was the most? Okay. What controlled the number of times that you had to do it? Did you notice? Yeah, Holiday?
How many times it took you to get back to your original, or how many times you could until you got to a simple integral.
Okay. All right. And so could you tell just from looking at a problem that it was going to have to be done more than once? How could you tell?
If you had a polynomial and it was raised to a certain power, you knew you'd have to do it at least that many times.
Okay. So I think the highest polynomial I gave you was x squared, which you had to do twice. But then if you had an x cubed, it would take 3, x to the 4th would take 4. So tabular integration is a subset of integration by parts that only works on the PET part of Lipit. Okay? All right, so imagine that, normally you would do Lipit, but if you only had PET, okay, so you don't have a logarithm, you don't have an inverse trig, you have to have a polynomial, and then an e and a t. Okay, if we have that, we can use what's called tabular integration, which is a condensed method of integration by parts, so that you don't have to repeat so many times. Okay, it's just condensed down. So let me show you how this works. So suppose you had x to the 4th times e to the negative x dx. Traditional integration by parts would require you to do that process 4 times because of the 4th power of the polynomial. So this is a PET. We're starting with a polynomial paired with an exponential. And so we're going to condense the process of integration by parts down into something a little simpler. But we still start with the same setup. Okay, you identify your polynomial will be in the x to the 4th position, and e to the negative x dx would be in the other one. And the process, you just start the same. Okay, we do a derivative. The derivative would be 4x to the 3rd. And we do an antiderivative. And the antiderivative is negative e to the negative x. Now, instead of moving then into integration by parts, what we're going to do is we're going to extend this a little bit longer. And we're going to repeat the process. We're going to do the derivative again. And so the derivative of 4x to the 3rd is 12x squared. And the antiderivative is positive e to the negative x. And then we do it again. And so rather than repeating the entire process over and over again, this is why it's called tabular, is because you're creating a table. And so in fact, I'm just going to create the whole left column of my table by taking as many derivatives as I can until I run out. So eventually I'll run out. And so the next derivative would be 24x. And the next derivative would be 24 as a constant. And the next derivative would be 0, and that's when I've run out of derivatives. On the other side of the table, I'm doing antiderivatives. Are you ever going to run out of antiderivatives? No. Why not? It's a cycle. It's a cyclic. It's just going to keep going all the time. So then we have another antiderivative, which would be back to negative e to the negative x. And another antiderivative back to a positive e to the negative x. and then another antiderivative back to negative e to the negative x. Okay. Now in the original integration by parts method, we start our answer by pairing up this diagonal combination. And that's exactly how the next part of the integration, the next step goes. You're going to pair those two together. So that would be x to the fourth times negative e to the negative x. And then it was minus. Now rather than setting up another integral, which would be the next step, we pair up the next two. Which would be 12 x squared e to the e to the negative x minus, sorry, 4. I was looking ahead to the next one. 4x cubed, sorry. I'll show you. Okay, all right, then the next pair, these two, negative 12 x squared e to the negative x minus and the next one 24 x e to the negative x minus, and then the last set negative 24 e to the negative x. Okay. Now, Abigail wanted to know why I was kind of writing it that way. This last term that we end up with is behind the negative, right? The one that's right there, that negative affects it. But then that one is behind that negative. And then the next group is behind that negative. And the last group is behind that negative. The negatives affect all the way through. So in other words, this negative here is going to get distributed here, but it also gets distributed there, and there, and there, and there. Okay, the negative gets distributed all the way through the equation. So how do you keep track of that as you go? Because first you end up with a single negative, then you end up with a double negative, then a triple negative, then a quadruple negative, and then on and on and on. So one of the ways that you can keep track of that is back on your original table. So I'm going to just clean up a couple things here so I have some space to write. Okay, back on your original table, you can keep track of it this way. Change this to this one. Oh, no. All right, so the first pair is fine. The second pair is behind a single negative. The next pair will be behind two negatives. The third pair will be behind three negatives. And the fourth pair would be behind four negatives. Now, you don't have to keep writing all the negatives like that. What you can do is you can say, well, I know that two negatives make a positive, and so you can just write that'll be a positive. Three negatives are still negative, so I can just write negative like that. And 4 negatives would be a positive, so you can write it like that. And so that's one way you can keep track of all the negatives. And so you would write your final answer this way. Okay, I'm gonna start with my first pair. So here's where I'm going to put my final answer down at the bottom. My first pair was x to the 4th times negative e to the negative x. So that's negative e to the negative 4th. Okay, my next pair, or my next term will be minus this pair, and then plus this pair, and then minus this pair, and then plus this pair. But even in you're adding, there's some negatives inside the pairings that you have to watch too. So I've got my first one, and it'll be minus 4x cubed e to the negative x. And then although the next one is plus 12, I'm multiplying the 12x squared by a negative e to the negative x. So it ultimately ends up being negative x squared e to the negative x. And then minus 24x e to the negative x. And then plus 24, but times negative e, so minus 24 e to the negative x. And because this is the end of a tabular integration process, what goes on the end of every integration? Plus c. Okay, what do you notice that all of these terms have in common, other than the plus c? They all have e to the negative x. What else? They all have negative. So it is very common for you to see this answer with that negative e to the negative x factored out. So if you take out negative e to the negative x, that will leave you with the polynomial x to the 4th minus 4x to the 3rd, plus 12x squared plus 24x plus 24, end your parentheses, and then plus c at the very end. Now I went through that very slowly and detailed so that you could see how that whole process goes. It really is faster than doing 4 rounds of tabular integration by parts. The biggest danger is keeping track of the negative and positive signs. The other danger I see is some people getting mixed up in their table and doing like derivatives all the way down on both of them or something like that. Okay, those are the biggest danger areas. So I'd like to try a second one with you so that we can practice the process. Again, this is the consolidation of integration by parts. It only works on PET combinations. It doesn't work on ET combinations. It has to be P. You have to have a polynomial. All right, so let's try x to the 3rd times the sine of 4x dx. Okay. Traditionally, if we did regular integration by parts, this would take us 3 iteration rounds. Okay. This one, let's make it interesting. Let's do 3x instead of 4x. That will give us some interesting math. Okay, we're going to set it up. The polynomial will go in the x cubed, and the sine 3x dx will go in the antiderivative column. I think I'm just going to do all my derivatives first rather than one at a time. I'm just going to go straight down the column and do all the derivatives. So that would be 3x squared, and then 6x, and then 6, and then 0. So why is it important that you have a polynomial? So it finishes. Yeah. If you start it with a logarithm, it won't finish. It just keeps getting worse and worse and worse. If you start with an inverse trig, it definitely gets worse and worse and worse. A polynomial is the only one that will descend all the way to 0 very nicely for us. And then it's also important that you have an E or a T at the end because they're the cyclic ones, okay, and they won't ever run out. Okay, now we work through our antiderivatives. We're going to have to watch the anti-chain rule as well as we go here with that 3. So the antiderivative of sine is negative cosine. And the anti-chain rule says we have to divide by 3, or I like to multiply by a third. Right, the antiderivative of negative 1/3 cosine is positive sine, is negative sine. And I need the anti-chain rule again, which will give me 1/9. The antiderivative of this is positive cosine. I'll need the chain rule one more time to give me 1/27. And then the antiderivative of that is positive sine. And the anti-chain rule giving me 1/81. Now your pairings starts positive, then goes negative, then positive, then negative, and then we run out. So the first pair is a positive pair. So then I think we're ready to start our answer. So we combine diagonally, and we'll have negative 1/3 of x cubed cos 3x. Now will the second pairing be positive or negative? Okay, look at how you're combining it here. Okay, will the next pair be positive or negative? It'll be positive because you have a negative with a 3x squared, but you have also a negative with the 1/9. So that will give you positive 1/3 x squared sine 3x. Okay, the next term will be positive 6/27, which is reducible. You get 2/9 x cos 3x. The last pairing is negative. So we'll have negative 6/81, which also is reducible by 3 to 2/27 sine 3x, and then plus c. And so it would be common to write this answer grouped according to the like terms of their trig values. And so you would maybe rearrange this and have negative 1/3 x cubed cos 3x, and then put the 2/9 x cos 3x next. So you're rearranging them according to their trig common terms, and then put the sine terms next. So 1/3 x squared sine 3x minus 2/27 sine 3x plus c. And then you would partially factor. And so you'd take the cosine terms and take out what they have in common, which would be cosine, also a fraction of a third, also an x. So you could pull out 1/3 x cosine 3x and leave you with negative x squared plus 2/3. And then for the last part, you could take out a sine 3x and again a common factor of a third, So 1/3 sine 3x. That would leave you with x squared minus 2/9. And then plus c. So it's pretty common when you have a trig, even though the trig isn't common the whole way through, you can partially factor terms that do have it in common.